Okay, so thank you very much for coming. Another seminar. This one is the first one of the year. So let's hope a very good season of seminars this year. Just to remind you, now we are missing, we have a lot of spots still to fill this month. So remind to your people in your team or yourselves. So if you want to give a seminar, just reach out us and we will schedule one. So we keep this running until summer. So today we have a special speaker. It's a guest researcher, Stergios Zarkogiannis, and now Godson. He's a visitor scientist in the interview group, and he will introduce him.
Thank you. Welcome everybody. Stergios is a paleoceanologist, basically. He's originally from Greece, but he's been working during his career in the University of Cambridge, and right now is located in Leibniz Center in Bremen, I think. Even more steps in between. And he works in a research area which probably we eventually interact, but we don't have many experts here at Imedia, which is studying very long-term processes, climate scale processes in the ocean, and how probably the currents and also biodiversity has been modified over the time. Basically, he does this with different techniques, but mainly studying sediment cores and particularly coccolithophores. Thank you. Thank you very much for coming and just illustrating here this research area. And for sure, anyone that afterwards wants to have a chat with him, and even along the afternoon, you are welcome. Just contact at the end of this presentation. Thank you.
Thank you very much for the invitation and for having me here. It was a great pleasure to contact Godson when I was wondering about what happens to these planktonic organisms and how do they orient themselves in the water. And then I found that there is another person on the planet that does this, and I said, okay, maybe I need to contact him. As Godson said, I'm working with plankton and I'm working with non-motile organisms. So they are passively finding themselves in the water. And I've been I started my research with planktonic foraminifera, which are like a sort of calcifying plankton, zooplankton. But then I was really interested, I found like a process and I wanted to check whether this applies to phytoplankton, calcifying phytoplankton as well. So this is why I then moved to coccolithophores. And now I am at the moment at ZMT working with corals. They're not planktonic, but they do still calcify, and I would like to see like calcification in total, because it's a process that affects our climate and the concentration of gases in the particularly CO2 in the atmosphere. I will go through my background a bit. So I did marine sciences as my bachelor, so I'm always very glad to be around other marine sciences. Marine scientists. I then did my master's in environmental coastal engineering, because during my undergrad I was mostly interested about coastal sedimentology. But then in terms of education, after doing like a bit of marine sciences, I had like a change in my life and thought to study architecture. So I did like second degree, but then I think I was mostly like attracted to science. So I came back and I did a PhD in paleoceanography at the University of Athens. And in terms of professional experiences, like I started in Bremen, in the repository, because this is where the IODP repository is. IODP is like the International Ocean Drilling Project, which is like an international organization that has been collecting deep water sediments since the 1970s. And like there are 3 depositories. The one is like located in Bremen, the others in like USA and Japan. And then this is where it's all started with me in paleoceanography. I then So it's not a linear thing. It goes like back and forth. Anyway, this was like during 2010. I did my break. I did the second degree, but then I came back after finishing my PhD, and I applied for an independent fellowship in the UK, and I got this Royal Society Newton Fellowship for Oxford, where I stayed for another couple of years as a Marie Curie fellow. Working here mostly with coccolithophores, and now I am a Humboldt Fellow at ZMT at the Center of Tropical Marine Research in Bremen. So I went back to Bremen again. And so what made me really interested was that while I was working in Bremen, I came across this process. I had to work on a core where I would like weigh the single cells. So these are, I'm mostly working with fossils, which are like the leftovers of these foraminifera, these calcifying organisms. They are, as you see, in the micro scale. And then in order to weigh them, so what I do is like I sieve them and I pick 50 of a certain sieve, so between 300 to 350 microns. I do an average, and then I have like an average cell mass. So this is what I had to do in one core. I will show you the result later. And the idea was that these organisms are building heavier cells during glacials, and that their skeletons become lighter during interglacials. This is an inverted scale. And the major theory behind this change in their calcification was that it's because of the change in the acidity of the water. So when we have glaciers, the water are more alkaline, less CO2 in the atmosphere, so they are able to calcify heavier when the waters become during interglacials. We have acidification because more CO2 is coming to the atmosphere, so they are supposedly become later. But they came up with this idea because they only studied one glacial cycle, one interglacial cycle. But if you look like this is the wider record, like the widest record that we have from this particular planktonic foraminifera species. And that's the only one that we have that goes back to 1 million. We see that this fluctuation in the weights do not always go hand in hand with the concentration of CO2 in the acidity or in the atmosphere and the acidity of the waters. And this is what kept me going, particularly when I had to work on this core, again, sieve these and take average cell weights. This is the average cell weight from near equatorial side. And then I saw no cyclicity in the signal. And this is like two glacial, interglacial cycles. So then I could not finish this work because I didn't know how to explain this. And then I had to come up with another story, like to explain what it was recorded. And then I went out to review all what we have in terms of weights globally between at least the last glacial interglacial cycle. So I just like created this graph here by making the delta weight. So weight glacial minus weight interglacial. And then I found that there is like this latitudinal pattern. So this is latitude, these are the tropics, and this is like the change in weight between glacials and interglacials. This is the other hemisphere. And then I saw that this change was greater in higher latitudes, and the change between the glacial to interglacial weight is like minimal, almost absent during at the equators. So I said, okay, maybe this is a density signal, and just because these areas here are like, because of their inclinations, they get like stable energy from the sun all over the time. The oceanography here is stable, whereas if you go in higher latitudes, we have like these insolation changes, which changes that changes the densities in the water, and maybe this is why we get this higher variability in this latitude. So this kept me into going, and I said, okay, how can I test this? So I needed to find a way to calculate the buoyancy. So that's like the force of the ocean that each single cell for planktonic cell feels from the ocean. So I use Archimedes principle, which says that the buoyancy is equals to the weight of the displaced liquid, so the amount of, like, let's say, seawater that this animal displaces when it lives, when it's alive, which means that it's mass times gravity, and the mass, it's actually the density of the medium, the density of the water, to the displaced, to the displaced volume of the water. The displaced volume of the water is actually all the outer volume of this alive cell. So this is like actually the total volume of the cell here. And what I needed was the medium of the density of the medium, which also has to be equal to the density of the organism, because if these two densities are different, then the organisms should like regulate until they find like an equilibrium. And to get to these total volumes, I use tomography, and this is how I calculate using these 3D models, the total volumes. And to get to the density, how do we get to the density? We need temperature and we need salinity. How do we get this? We can get this chemically if we analyze the cell. So if you do like there is like this magnesium calcium elemental analysis that you do to have like an indication of temperature. And then you also do isotopic work on that, particularly the oxygen isotope, which is like a function of temperature and salinity. So if I have a proxy that can with which I can calculate salinity, then I can go and subtract this from the isotopes to get to calculate temperature. Sorry, I can subtract temperature from the isotopes to get salinity, and this is how I calculated the density. And the buoyancy. And then I found like this nice relationship between buoyancy and the mass of the shell, this individual fossil. And that you have like higher masses during these darker dots are like points, glacial points, and these are like interglacial fossils. And you have like this relationship between buoyancy and mass. And I said, if this is true, then you don't even need to calculate the volume. Then what you need is also just to have like an indication of the density of the water, and then this has to correlate with the mass of the fossil. So this is what I do. I reanalyzed some already existing literature data, and these are weights of cells that they are between 300 to 350 microns, and these are like weights of cells that they are between 250 to 300 microns, so they are smaller. And what this graph says that they are, and this is a good evidence that the smaller these animals are, the lighter waters they live in. So this is the density here. And as they become older and bigger, they dive into deeper water. So this is like direct evidence of a theory that we had, that these animals, as they go deeper into the water column. And we couldn't find like a mechanism, like many evidence, and this is like one of them. So the idea now behind this is pretty simple. In case of an interglacial ocean where we have like all the ice melting, you have like all these ions that they are in the water placed in a different volume. Whereas if you take pure water out to make like continental ice and sea ice, you increase the density of the ocean. This then denser ocean exerts greater force because there are much more many atoms there, greater force to any particle. And for this particular like protist to live at certain depth, my idea was it had to become heavier in order to go back to its optimum depth. So actually, like they regulate their because they cannot swim. So the only mechanism that I thought they have in order to regulate themselves in the water column is by changing the weight of the skeleton. And I did most of my work on sediment cores, and this is like data that go back to at least 2.5 million years in total. But then I said, okay, if this is a process that has been working back then, it must be a process that it is working right now. So I said, instead of working only on old material, I should focus on surface sediments, which are actually indicative of, let's say, modern conditions, and I can like compare them with modern oceanographic data. And so this is like, I used this data set from the equatorial, from the central Atlantic across the mid-Atlantic ridge. And I weighed all these different species, and then I found that their skeleton is a function of depth, which makes sense. So the deeper they live, the heavier their cell must be. And this was a very good indication, because it still I had to fight the theory against acidification and calcification, which is still the prevailing one. So I always had like inside me like the question, is it really a chemistry thing or is it like a physics? And then I said, where can I disentangle this physical to chemical signal? And this is when I thought, okay, I should do this like if I do in depth. And then if I have like this change in the weight in depth, this is clearly a physical signal, because the acidity of the water increases with depth. So no, decreases with depth. So the ocean is more increases with that. Sorry, the ocean is more acidic towards the deep, and this is like the carbonate ion concentration. It's higher here, and then it becomes low. So if this was an acidification issue, then the deeper animals should have had lighter cells, because they couldn't calcify heavy. But they do the opposite, they are heavier. So despite them living in acidic environments, they are still able to manipulate the liquids around them, the environment, to produce more calcite, to produce more skeleton, to dive down to their depth. And yeah, this is where I said, okay, now I convinced myself at least that this is the case. And then I said, is this a process that happens to other calcifiers? Because not all calcifiers are able to manipulate the water. Like planktonic foraminifera do have like enclosed vacuoles that they manipulate the chemistry, but coccolithophores, they are more in contact with the environment when they build their skeleton. So I said, like, is there any indication that coccolithophores now calcifying phytoplankton becomes heavier as we go deeper? And indeed there is. And so this is like what I find out. So this is like a global collection of phytoplankton, 85 different phytoplankton species, and this is like the inorganic to organic ratio. So the inorganic carbon, this is calcite, increases with depth as well. So this is depth, and this is like here latitude. So we have like also higher calcifying species, planktonic foraminifera species at depth, where the waters are still more acidic than the surface. So this was like another indication that, yeah, there is like definitely a buoyancy regulation mechanism in their skeleton. Yeah. And this is something to show that, as argument again against the acidity and the availability of ions, because this is what acidity does, it just changes like the concentration of the ions that they use as building blocks for their skeletons. It's like as we have today, for example, today this is the limit up to which we can construct, and this is not because we don't have enough material, it's because we have physical limitations. And yeah, this is what I think happens also to them constructing their cells. So I said, okay, if this is true, and then there is like a function, there is a relationship between calcification and skeleton formation and density, seawater density, then just weigh few of these specimens, then we can reconstruct the seawater density of the ocean, and then maybe we can do large scale paleoceanography and oceanography. Yeah, actually paleoceanography. And then I went and studied three cores. So the one that I already did in the beginning. So this is like the green core that I already showed you. The blue one is like from the north, and this is like work that I showed you also in the first slide from this record that goes back to 1 million, but I cut it here at 200,000. So these are like two climatic cycles, so 200,000 years. And then I also got another core from the south to see what they are doing. And I plotted the weights actually, and I also used like my function to calculate the density of these waters using my proxy. And I just wanted to see what these weights are doing together in the Atlantic. And then I found like these, I think three very interesting things. The one is like the weights that come from the equatorial ocean are like the lightest, which fits because the equatorial ocean is lighter. It gets more precipitation and it gets higher temperatures. So that's a good indication. And this is like they have been pretty stable. The other interesting thing is that there are two times which the weights converge from these different areas. And not only they converge, but they converge to the same number. So around like this density. And this is like I said, if there is like a conversion in the density of the different Atlantic basins, it means there is no circulation because there is no density gradient to drive any circulation. And I managed to find other chemical evidence that there are indeed these periods in time that they can fairly well correlate in terms of like age models that the circulation has been sluggish or even like not existence in the Atlantic. And the other interesting thing is that after the last deglaciation, so this is like the last glacial maximum was about 20,000 years before now. So after like we start having the ice melts, the density gradients in these three basins have been not great. There is not much variability. And this means that the circulation in the Atlantic has been slower. And this is what most people also are finding, that the Gulf Stream has been becoming more and more slower after the last glaciation. So I thought that it would be very nice and easy and very not time consuming and cheap just to weigh these fossils and then like make large scale oceanography. And yeah, this is the work that I am doing now. I just want now at the moment I'm working in the Red Sea, and the Red Sea has a really nice it's an end member because it's a very dense oceanic basin, and it has like this very nice density gradient towards like the opening to the Gulf of Aden here, and there is like where you have like lighter waters coming in, and you have like denser waters here in the northern part. And then I want to see if the weights are actually following this really nice density gradient. This is work in progress. And then the other application, which I'm going to be hopefully starting sampling next week, is like to look at the strength of the current itself, because this is here a cross section of the Gulf Stream. So this is Florida, and this is the Bahamas. And for any circulation to take place, you have to have like this density gradient. So like for geostrophy to work, you have like this denser dense like isopycnals coming towards the surface, and the inclination of these of these isopycnals is a function of the velocity of the Gulf Stream. So my idea is to try to see now whether I can go and I'm gonna do some in situ sampling here to see whether I can reconstruct whether their calcification fits with the densities and whether they can be like an indication, and whether by taking like organisms from these two different, let's say, locations, I will be able to find a function that can get me back to the velocity of the Gulf Stream. And if this works for today's organisms, then I can just take sediment from below these two locations. So this again is the Florida, and this is like the Bahamas, and this is the Gulf Stream in between. There is a very nice, so this is like the line of 27 north. It's like where the Gulf Stream squeezes through this strait, and when you have like the stream squeezes, it has like the highest velocities, which also means that they have like the deepest gradient. So it's a very nice area to be looking at. And then if this works for today, then by having like sediment cores from these two different regions, we might be able to, let's say, pretty economically reconstruct the velocities of the Gulf Stream. Fingers crossed. Yeah, this is more or less my presentation. I'm not sure if I did it maybe. Did it quickly on time, I'm not
Yeah.
sure. Yeah.
Thank you very much. Interesting. Any questions from Stergios?
I had a question. So actually, I'm not sure I understood completely the idea. The idea, if I understand well, is that the thickness of the shell of the foraminifera is dictated by the fact that they want to be buoyant, neutrally buoyant, sorry.
Yeah.
Right?
Yeah.
And therefore, depending on the density of the fluid outside, they will grow a thicker or thinner shell in order for the average density of the organism to be matching the thing outside. And therefore, you can use this as a proxy for blah blah blah.
Yeah.
Okay.
Assuming that the protoplasm, the density of the protoplasm, because
We know
it remains stable because it has to sustain the same life.
that I
Yeah.
can. I have absolutely no problem with that. The so I didn't really understand the evidence for this, meaning that the fact, for example, if you find thicker organisms at depth, could just be due to a bias in the sampling, meaning that they will get there more often and faster than the lighter ones, right? And therefore, just the fact that they are there and you find them there more abundant doesn't mean that they, in other words, could it just be that they're just falling down, right? And therefore you find them more often there because they get there faster than the lighter ones, right? Do you understand what I'm trying to say?
Yeah.
In a sense, you see that I'm not disputing the observation, I'm disputing the interpretation of the observation, which is based on the assumption that they live there permanently.
Yeah, this is so these are here. They are average calcification depths that they have been found in these areas. So this is like when they go out with the nets. Okay, and floating stuff float everywhere, and like even like the ones that they are like living deep enough, it might be that they get some sort of food, prey, or that is like light enough that can like make them go up momentarily until it's consumed and then they go back. So things are found everywhere in the water column, but there are like some particular depths that these species dominate. So they have like an optimum habitat, and this is where you find most of them. And this is like these are like they are. That's what I mean by
So just to
Yeah.
jump in this, so it's not the same species.
No,
Yeah, so you are just comparing different species at different levels.
yes,
Okay.
yeah, these are like different species. So this is like the lightest one.
Hmm.
And then as you go here, this is like the deepest. And they also have a change in morphology, which we can happily discuss as well, because the more like rounded and bubbly they are, the more up they go in the water column. But these are like, yes, different species that they are found on different depths. So I just like picked 50 of them, weigh them like on average, and then I found like a different. Yes.
Mhm.
Yes. And this is the same here with coccolithophores. So these are like, this is an average though of the different species, because coccolithophores are like nanoscale and they're a little bit more difficult to observe, but this is like an average of 85 species total. Like this is a global collection. And this is only latitude, and it's like all the data that we have. Like I think this is some model. I'm not sure exactly, because this figure I got from a collaborator who's like better in calculating coccolithophores than me. But these are also different species, but they are also averaged together to give us like an average inorganic.
Do you know if there is any type of plasticity? Meaning, for example, if I were to do an experiment where I pick these guys and I try to grow them in different seawater of different density, for example, would they adapt to a certain level to that density?
Yeah, and that has always been my problem with cultures. It's like you cannot assess this with cultures, because the organisms there are lazy. They get what they need. They don't need to put like a buoyancy regulation mechanism, because they have enough light, they have enough food, they are happy growing. And yeah, I did experiments myself, like keeping salinity the same and changing only temperature, and also the opposite, keeping temperature and changing salinity. But then this again is not a density regulation mechanism, because then comes like other like physiological processes in terms of ion availability. And so although I did it, I don't trust them, because it's like there is only up to a certain level that you can find with cultures, and like how they behave in the wild. Yeah, specifically like for buoyancy, I think it's a different story. Yeah.
About your future work, I'm sure if I understand well, so you, depending on the buoyancy of the shells, you have the density and then the velocity, right?
Yeah.
And your idea was to reconstruct the velocity in the past, right? The paleo. So how do you know when you will take some sediments in the sea bottom? How do you know at which depth they were?
Yes. So this is the major assumption here, that they always have been maintaining the same depth. So they have which is not true, I know, because they changed, but it's fairly stable. So I assume that certain species always live at 50 meters. So when I go 50 meters here and 50 meters here, I will find ideally the same organisms living, and the only change will be their cell weight. And then I assume that they have always been living like this particular species, because species they change in time, and there is like a limit to time where we can go. For example, like there is only one species that we have since the Miocene, which is about like, let's say 15 million years, that has been living ever since. So I assume that certain species has always had its certain depth. Yeah, which is I know it's an assumption. Right.
I was wondering about it surprises me a little bit that given a species can maintain a kind of an optimal depth, because my understanding is that these species are also, I mean, the individuals are growing and they are adding chambers, right? So they change in size and probably also in shape.
Yeah.
So even so, they can still keep the same kind of optimal depth. And how do they? So in that case, if you look at the same species at different stages, will they change the density of the shell to account for differences in shape and size?
That's a very nice and interesting question, but I think nobody who is working with size don't want to hear about buoyancy regulation using size. My idea is that they do, because they know how to. There are indications, for example, there are in the Miocene some periods that the organisms become very, very small. And in my interpretation was because they were trying to the water is becoming so dense that they had to become smaller, because they couldn't become heavier. So they just become small, and then they go down, they dive down, or they maintain the same depth by becoming smaller.
So sorry,
Yeah,
when they become smaller, it means that the ratio of the shell to the cytoplasm is high. Right? So they
ratio of
I don't know, so that they increase the proportion of inorganic stuff by growing small.
I haven't thought about it, but I was thinking more in terms of because the buoyancy that they feel is a matter of the projection area. So if you project more, you feel the ocean more, so you get more buoyancy. So if you shrink, you just go deeper. Like you feel the ocean less. So
Okay.
that was my idea behind changing shape.
Usually I mean, people here will know better than me, but the usual assumption is that the bigger you are, the faster you sink.
If you are heavy,
That depends on the ratio between the weight of your shell
That's
and
what
your
I-
internal. If your shell is the same, it has the same weight, then I would assume that larger volume will float more. But if you have more shell per volume inside, then I would say that the smaller ones will.
I think this maybe, for example, this is the buoyancy thing. So if you assume that the mass here, the density of the organism remains the same. So if you change the volume of the organism, you change its buoyancy. Yeah, so this is something that I haven't worked. I have thought about it, but people don't want to hear about it. So I have been sneaking it into papers here and there. But there was also another thing in your question about
shape.
shape and something else you.
I tend to ramble.
Sorry.
But yeah, about this, have you seen any pattern in how different shapes maybe different shapes are located in particular
Different, yeah. So this
so-
this is shape which goes deep, and it's very nice. For example, here, because this organism lives close to the pycnocline, and it's very nice because if you look at its cell. So if you live close to the pycnocline, small changes in your density, can be like major changes in the depth where you live. So they regulate their calcification so well that they don't find themselves somewhere that they can just go back and go so much up that they just lose themselves. So what they do here, they just do small mountains of calcite, just so that they play with where they want to live. Again, this is my interpretation, but this is like something which is very typical for these organisms, that they live close to the pycnocline. And the more you go up, they become more bubbly, and what is very interesting is like in order to go even shallower, they needed in time and in their evolution to have spines. So if you don't have spines, you can only go up to a certain depth. If you want to go shallower, you have to have spines, because these spines, they produce something. Because although it's an extra weight, the way that these spines, I don't know, are doing something with the water that gives them like a positive buoyancy. But yeah, there is indeed a shape, not so much studied, a bit studied, but yeah, shape has been fairly well studied, yes.
So, just to jump in, I will assume that I don't know much about their life, actually, or their biology, but I will assume that a calcifying organism, unlike other organisms where the buoyancy is regulated by back walls or some other things, here the regulation is calcifying. But I would assume that this is just a one-way process. This is you can increase your weight, but you cannot decrease it unless you increase your volume. Is that, I mean, they can do an additional blob or whatever it is, so they increase their volume, but the calcium that they have already fixed, that will remain over there. Is it like that?
Yes, and yeah, this is a tricky bit, because they are definitely not stable at a certain depth, because they can regulate their buoyancy with gases. They do that by using their metabolic gases. They store them somewhere, and then this gives them like an upward movement. But I think this mechanism actually is mostly about finding the deepest that you can go.
Mhm.
So because they can go up by producing gases, but what if they want to go down? So like they lose the gases and then they have to go down, but how much down can you go has to be dictated by the skeleton weight. The other idea would have been to reduce lipids to go even more down, but I think because lipids are like very much associated with energy storage, you wouldn't sacrifice lipids. You wouldn't just discard lipids to go down. You would have thought of another mechanism if you wanted to go down and keep your lipids. And this is also another interesting process that is called something which is called gametogenic calcite. So whenever they have like their gametes and they increase their lipid content during the gametogenesis, because they give like one lipid molecule to each offspring, they secrete an extra layer of calcite, which I interpret as their way to maintain depth. Because if you increase the lipid content, and lipids are not compressible, they can just drive you out of your equilibrium pretty fast, because they can like decompress pretty easily in the water. So they have to, yeah, I think they have to find a mineral which is more stable and more stable matter and they can also dissolve this. So some of them, they can also resorb the spines and use the calcite to make gametogenic calcite. I don't think that there has been cases that they have dissolving they have seen that they dissolving their already made shell. But yes, so just to conclude, I think they are doing what they are doing because this way can give them the deepest that they can go into the water. And if they want to go up, they can use their gases. But if they want to go down, I think they have only to use skeletons.
Just for me to understand, is it correct that you essentially believe that these organisms are regulating their, so you use classification in order to essentially get thicker and stuff, and then find what will be the optimal depth, which may change because there is a change in the density of the water. So, and this is due to some environmental factors like being an glacial age versus obviously there. And but what I was wondering, so I have no idea about the biology of all that, but so the moment in which this happens, so these are change which affects so the density of the ocean, which impacts everyone equally, right?
Yeah.
So I was wondering, so if there's a change which hits everyone, then I would say that, so why should I be the only one searching for like another optimum? So I would imagine that everyone follows me, just so is not really following me, but you know, it is a change which affects everyone. So I was wondering why the optimum would be somewhere else. So I started. So in the sense that, so I have no idea if it is a matter of finding other organisms at the same depth there. So if everything changes equally for everyone.
Equally, yeah, but it's like what I've been thinking about that is like what doesn't change is like you want to maintain your same depth because you want to maintain the food, and the food that they eat, it comes from light because they consume mostly phytoplankton, and phytoplankton is like sensitive with light. So this is like ideally like phytoplankton also needs to go to certain habitats because there it gets this specific light that it needs. So these is the ones that they try to be, I think, more stable, and then the animals try to maintain their prey stability, and they try to be stable themselves. I don't know if I answered this.
Yes, but so essentially your answer also suggests that you might have other ways of checking your hypothesis by looking at what happens to the other guys if they're actually able to at the same time point to be somewhere else.
Yeah, this is why I want to work with, because this is a story that I've been doing only from sediments, and it's like nothing. And this, like what you find in the sediments, is like the organisms that they have been more successful in their time. They are the ones that they have been more down there to be preserved, because there can be other many millions that they never made it there, or like they were not successful to be that big, because I also like constrain the size. But and there is some it's nice to work with sediments because like it's a sieve in terms of like, because you get rid of all the other processes and you know that you find that is like the most successful one and that you get like a clear signal. But then when you go to work in the water column, like here to go get some, this is where you find everything, and then this is where I don't know what makes sense anymore, but I'm looking forward to check. Yes. So I've never worked with actual sediment, like water samples. So it's only like I see part of the system because I only check the skeletons, which also have been.
Somehow, so my understanding now is that so there is this change, and then so this change induces, well, essentially someone has to make adjustments.
Yes.
To be better off.
Yeah.
And then these people are kind of catching up.
Yeah, and the ones who come and the ones who are the most successful, I guess. And these are the ones who I finally find preserved because they succeeded to be high in numbers.
Mhm.
Yes.
Okay, so you would be wrong to believe that. So there is this change, which is change of the density across the board, and then everyone is just scaled down by a factor in depth, and then nothing changes. So
Yeah, that's my assumption. I know it's not like that. Nothing is so ideal, but that's the ideal assumption. Yeah.
Thanks.
No, I was a related questions. So why some of the women want to stay down in their from the
Yeah, I mean, I think they just had to. I think every one of them preys on different organisms, and then if their food is up, they will have to somehow make it up there. But I think the fact that they find them at certain depths means that their food is there. So
So it's not phytoplankton with
yes.
or something else.
No, they feed on everything what they find, like bits of matter that they are dying, or like even like degraded material that they find. So like they feed with with everything that they find, yes. But yeah, my idea is that I think they do this because there's competition. So they found some space. Okay, there is food here. Maybe if I like manipulate my weight, I can just like go down there where nobody else can go, and then we can survive there.
And what is the time scale on which they will?
So they live about a month.
So
So yeah. So how exactly but again, this is an ideal model that has nothing to do with reality, because if you go up there, you have to work statistically with reality. If you go and you take some, and they are also patchy, like you go, even if you go with a boat, you sample there, but like what you sample might be like a desert, you find only a few, and then there is like a party going on which you never saw.
and you can have an upgrading event and then you sample everything that was done.
Yeah, you can do that. So it's just like, yeah, and then if you look at this and like a plankton sample, you find everything there, different sizes coexisting, like smaller coexisting with bigger. But still, size has been assessed, but the general buoyancy of these organisms hasn't. And it's also very difficult because it's like, I've watched videos of them, like if they incorporate one piece of organic matter, which is light enough, you can see them like as they do, this food takes them up. And until they consume it, they are up. And then when they finally consume it, they just like go down again. So it's just like, and it's like very random when you get them.
Now they praise or something.
They prey on phytoplankton and like whatever they find, and they get preyed by fish, yeah, or like copepods sometimes, these sort of things. Yeah.
Yeah, sorry, now when you said that you sample as in real check, or is there a way of checking if they are alive when you sample them?
Man, that's a good question. I think you can put some dyes to mark the living cytoplasm. That's true. I have to think about that, thanks, because I have to do the sampling the next 2 weeks. But I think it's also that you can see that they are, I don't have a picture because I work with all dead material, but when they are alive, they are colorful. You can see that cells are very well filled with organic matter. And you can also see in the net samples, some shells that they are definitely, they're empty, and you know that these are like very dead. But how alive they are, that's a good question, because even if they die, these colors within the cytoplasm still remain. But whether the organism is still very alive, that's a thing, I have to think about it.
Yeah, because they can sing, no? So maybe you find them there just because.
Yeah, it's true.
Yeah, so we can leave it here. Yeah, thank you very much, Stergios.
Thanks again for the